My name is Arul Lakshminarayan. I'm sitting in southern part of India in Chennai at IIT Madras. So welcome everyone. We have two interesting talks. The first by Lorenzo Maccone from the Universita the Pavia, Italy, is going to be talking about quantum time and quantum space time. Lorenzo, you have about an hour, so please share it. You could start.
Okay, thank you for the kind invitation, and let me share my talk. Okay, I think you can see my slides.
Yeah.
So yeah, I'm going to talk about quantum time and quantum space-time, and in particular, I'm going to talk about this geometric event-based quantum mechanics, GEB in short, which is a paper we just posted on the archive last week. We just submitted it yesterday. So what am I going to talk about? Well, I'm going to talk about time in quantum mechanics and how to give a consistent formalization of time based on conditional probability amplitudes, based on quantum states, basically. And then this new result we have about a new way to do relativistic quantum mechanics. So to build up on this quantum time thing to create a quantum space-time. So something that
Is it only me or Lorenzo, you're breaking up, but I'm wondering whether it's just for me. Can the organizers confirm if things are okay? Yeah, so Lorenzo, there seems to be an audio issue. Okay, I guess he's rejoining.
Okay, sorry. You're hearing me now?
Yeah, much better.
Yeah, sorry. Something happened to my connection. I'm sorry.
Okay.
So where did you lose me, this slide?
Pretty much at the beginning.
Ah, sorry about that. Okay. Let's go back to what I was saying. So here?
No, wait. I can't see anything. I don't. Please share again.
Okay. Sorry, there is a problem. I hate these Zoom talks, really.
Yeah.
Okay. So I think you can see me now.
Yeah, we can now see.
So did you hear what I was saying about this slide?
No.
Okay. Okay. So you lost me really at the beginning. Okay. So let me start again. So I'm going to talk about time in quantum mechanics and how we can give a consistent formalization based on conditional probability amplitudes, basically quantum states that can be used to describe time, quantum time, and then expand this to a new result, which we just posted last week, about a new way to do relativistic quantum mechanics, building on that. And so since people may not be familiar about quantization of time, let me start from the non-relativistic case first, which is the simplest thing. And then we can talk about relativity later, what happens in relativity. So what happened?
Sorry,
yeah,
Lorenzo.
Sure.
I mean, I'm only seeing a slide with a clock at the bottom right. Is there supposed to be anything else?
Yeah, it's supposed to say time in quantum mechanics. No,
On the
you
top.
don't see that?
Can you just change the slide? Let's just see whether it moves.
Okay, there's something wrong.
No, nothing is happening. It's oh, okay. No, it stopped sharing. Yes.
Yeah, I really, really do not like doing this things. Okay, let me try again. Okay.
Yeah. Yeah.
This
Now I
is
see
not the
new
right
approach to
thing. No,
relativistic quantum mechanics and archive number and so on.
yeah, but that was not the right
That's not what you want.
window.
Okay.
So, okay. I apologize. This is it. Okay. Now you're seeing the slides and they're moving.
Yeah, yeah. Now it's fine.
Okay, good. Sorry. Okay, so what happens in quantum mechanics? Where does time come in quantum mechanics? Well, if you think about it, time is just a classical parameter that appears in the Schrödinger equation. So this is one of the postulates of quantum mechanics, and time is just some parameter that appears there. And what does it say? It indicates what is shown on the clock on the lab wall. So you're doing an experiment on the optical table, and you have a clock somewhere in your lab, and it's a classical clock, and this classical clock indicates, gives some time, which is what appears in the Schrödinger equation. Of course, this classical clock is a classical system, but classical systems do not exist. If you want to give a consistent theory of quantum mechanics, in which everything is described by quantum mechanics, you should not need in one of the postulates of the theory some classical system. That is not consistent because classical systems should appear as a limiting situation of quantum mechanics. So this state of affairs is not very nice. To need a classical clock to write the Schrödinger equation. So we can define time as what is shown on a clock. This is a good definition of time because it's, for example, the proper time in relativity. And then just use a quantum system as a clock. That's a very simple idea, and it works pretty well. For example, you can think of a quantum particle on a line. The position of the particle along the line tells you what time it is, or any other quantum system can be used as a clock. Not any, but many quantum systems can be used as a clock. At this point, you can assign a Hilbert space. For example, for a particle on a line, it's L2 of R, or other Hilbert spaces, depending on your system you choose. And then if you do that, then time arises just as correlations. Actually, it's entanglement between the system on your optical table and your clock, which is now a quantum system. So you can have entanglement between the two. And this is actually a proposal that has been in the literature for many years. It has been rediscovered many years. For example, by Page and Wouters and Aronoff and Kaufer. These are just two of the main papers that describe this. So in essence, we have a Hilbert space for the system, which is the usual Hilbert space you find in quantum mechanics. And then you add to that a Hilbert space for time, which is basically the Hilbert space of the clock. And then you introduce a constraint operator J, in which is basically the sum of the clock momentum plus the system Hamiltonian. And then you say that all the physical states must satisfy this constraint, J psi equals 0. Okay, so it's basically a Wheeler-DeWitt equation. This psi, we use this double cap notation sometimes just to remind people that this is a bipartite state, because it's a state which is defined on both the time Hilbert space, the Hilbert space for the clock, and the system Hilbert space. Why are we introducing this constraint operator? Well, it's very simple. Using this constraint operator, we are saying that for physical states, the Hamiltonian of the system Hamiltonian, is the generator of time translation. So it's equal to the clock momentum, okay? This is the reason why we are introducing the Wheeler-DeWitt equation in this form, okay? And if you do that, you do get back quantum mechanics. I mean, it's a very small extension of quantum mechanics, because now time is a quantum degree of freedom, but you get back quantum mechanics because all you have to do is condition. So if you take this global state of the system and clock, and then condition the clock to being t, to showing time t, what you get is the state of the system at time t, okay? And this is easy to see because you can start from the Wheeler-DeWitt equation, from the constraint equation. And remember, omega is the momentum of the clock, h is the Hamiltonian of the system, and then you just project the clock on time t. And this means that if you write the momentum operator in the position representation, it's just a derivative, okay? But the position of the particle on the line tells you what time it is, so the derivative with respect to position of the particle on the line is equal to the derivative with respect to time. Okay, so you see that by conditioning, by saying that the clock shows time t, you get back the time-dependent Schrödinger equation. So the position representation of the clock is basically the Schrödinger equation. So that's good. And we can do the same thing with the momentum representation of the clock, and you get the time-independent Schrödinger equation. So this is how, in this framework, you get back quantum mechanics, just by conditioning. So basically, you have this global state of the clock and of your system. It's a sort of a state for a block universe. So X and Y are the degrees of freedom of the system, and T is the quantum degree of freedom. So this double cap psi, capital psi, is the Hilbert space for the block universe. And then if you condition, if you consider this at a specific time t0, what you get is the state of the system at time t0. This is what I mean by condition, okay? This is just a different way of saying what I was saying in the previous slide. So this comes about because if you take this Wheeler-DeWitt equation, this constant equation, and you look at the solutions take this form. It's an internal state between the clock that shows time t and the state of the system at time t. And of course, if you start from this state here and you condition on the clock showing time t, you get psi of s, the state of the system at time t. It's a conditioned state. This is something that not always is emphasized in quantum mechanics textbooks, but if you work on the Schrödinger picture, the state of the system is a conditioned state. It's the state given that the time was t. Okay, we'll get back to this because this will become important in the relativistic setting. So entanglement is important because if you just limit yourself to classical correlations, then you cannot get the same results. Without entanglement, you can either get the time-independent or the time-dependent Schrödinger equation. But if you want to get both, and of course, we do want to get both in order to get quantum mechanics. You need entanglement. So these correlations between the clock and the system really come out of entanglement. So what I've been showing to you up to now is a quantization of time, because now time is a quantum degree of freedom. It has its own Hilbert space, which is the Hilbert space of the clock. It can be entangled with the clock. So you have the global Hilbert space is the Hilbert space of the clock times the Hilbert space of the system. And of course, quantization of time, I mean, sometimes you hear that once you do a quantization of time, that means that time is discrete. That's not true. You have quantum systems which are continuous. So, and this is an example. The example I've given you, that I connected the time to the position of a particle on the line. That's a continuous quantum system. So this means that time is a continuous degree of freedom. And of course, this means, as I was saying, that you have a Hilbert space that is just L2 of R, the Hilbert space of the particle. And you can write a time operator, which is just a position operator of the particle. Remember, the position of the particle gives you the time. Okay, so of course, other choices are possible. This is the simplest one, which I've been giving. So the Hilbert space of time is the Hilbert space of the clock that defines time. Of course, other choices are possible, and we don't even need to introduce a particle. We can just consider the Hilbert space that defines time as simply a completely abstract purification space that has no real meaning. I mean, I like to think of it as the Hilbert space of the particle that defines time, because that helps me understand what's going on. But that interpretation is really not necessary. Okay, you're still seeing me and seeing the slide move, I hope. Hello? Hello? Okay, great, thank you. I have no feedback because somehow the window showing the audience went away. So, okay. So why do we want to do that? Why do we want to introduce a quantization of time? I mean, it's really not strictly necessary, but the reason will be clear in a minute when I start talking about relativity. I want to give a treatment of time and space which is the same. And as long as time is a classical parameter, this cannot be done. So, okay, let's now try to understand why it is difficult to quantize relativity or general relativity, even special relativity. What is the problem? What is the main problem? Let's look at what these two theories talk about. So if you look at the formalization of quantum mechanics talks about quantum systems. Okay, so for example, if you look at the first postulate of, if you look at the postulates of quantum mechanics, if you formalize the theory, the first postulate says that a quantum system is described by some vector. The state of a quantum system is described by some vector in a Hilbert space. And you see that it's talking about quantum systems already in the first postulate. Instead, if you look at general relativity or relativity in general, I mean, the theory is really talking about events, not systems. And quantum systems are infinitely extended in time. And of course, they are finite, or they may be infinite also in space. Usually they're finite in space. For example, you're looking at a particle. It's finite in space, but it lasts forever. So it's infinite in time. Or maybe you look at some quantum field and then it's infinite both in space and in time. Instead, an event is finite both in space and in time. Okay? So that's completely different situation. So we have modern physics is based on these two theories, quantum mechanics and general relativity. And these two theories really are talking about two different things. Okay, so this is perhaps one of the problems we are having when we try to merge quantum mechanics and general relativity into a single theory. So now, okay, that's fine. We realize this. Now, if we want to overcome this problem, we need to say which is the most fundamental concept. Is a system more fundamental, or is it an event more fundamental? What do you think? Well, of course, you can have two approaches. Consider systems more fundamental, and then you can have a general relativistic theory of quantum mechanics, where systems are more fundamental and general relativity is made of quantum fields. Or you can have a quantum theory of general relativity in which events are more fundamental. So you start from events, you somehow define a quantum events, and then you create a theory for that. Of course, if you consider systems that are more fundamental, then you can define an event as a derived notion, something that happens to a quantum system. So it's a derived notion. Otherwise, if you consider events that are more fundamental, then it's systems that are a derived notion. So a system, if a system is more fundamental, then an event is something that happens to a system. That could be a good definition. If instead an event is more fundamental, then a system can be considered as a succession of events. Okay, and this is the typical definition of system in general relativity: is a succession of events. Usually in quantum gravity, I mean, all the approaches I know of quantum gravity, there are many different approaches. They all consider, as far as I know, they all consider systems are more fundamental. So they take the first of these two approaches. Well, what we are going to do now is to instead consider the events as more fundamental. So we're going to consider the other alternative to this. And so let's consider relativity. In relativity, we have an event which is a localized region in space-time. So it's something which is localized both in space and in time. And then a system is just a trajectory in space-time. So it's a succession of events. This is what happens in relativity, but this is not what happens in quantum systems. And the problem is that the main technical problem is that in quantum systems, you need to have a normalization at all times. Okay, so you're normalizing over a foliation. You take space-time, you foliate, you divide it into sections at different times, and then you normalize at each time. Well, this normalization means basically that your system exists at all instance of time. It just doesn't go away. This means that, for example, if you look at textbook quantum mechanics, you can have, for example, interference fringes in space. This is an example. This, for example, is a situation in which you have a particle which is in a superposition of two Gaussian wave packets that counterpropagate, and they meet at certain position, and then you have some interference fringes where they meet. okay? So these are the two Gaussians going towards each other. They meet here, and where they meet, you have some interference, and then they just drift apart. Okay. So you see that the interference is just in space. You don't have interference in time. So this is because of this normalization of all time. And this is not very satisfactory. So we want to do a treatment of quantum events. We need a Hilbert space for events. And this is what we are going to do. So as I was saying before, in quantum mechanics, we are using quantities which are conditioned over time, okay? So I was talking about states because I was considering the Schrödinger picture up to now. So a quantum state in the Schrödinger picture is a state conditioned on time t. You're still hearing me? Is everything fine?
Yeah.
Great.
Yeah.
Okay, but of course you can think of going to the Heisenberg picture, and also in the Heisenberg picture we have conditioned quantities because an observable, for example, the position observable x is the position of a system given that time is t. Okay. So both the states and the position and the observables are conditioned quantities in conventional quantum mechanics. Oh, by the way, this is true also for quantum field theory. Also in quantum field theory, you usually work in the Heisenberg picture or the interaction picture, but things do not change. It's still conditioned on time. And of course, if you are considering quantities, physical quantities, which are conditioned on time, then they cannot be relativistically covariant. I remind you, covariance, I mean that relativistic covariance means that the formulas look the same in all reference frames. But of course, if the formulas contain t, then they cannot be relativistically covariant because t changes when you change reference frame. So there is no way you can have covariance if you use either the Schrödinger picture or the Heisenberg picture or the interaction picture. There is no way. So quantum mechanics and quantum field theory are not really covariant. Now, that's a surprising statement because people usually say that quantum field theory is covariant, and indeed it is, but you need to use a couple of tricks in order to recover covariance in quantum field theory, in order to somehow hide this conditioning that you have in quantum field theory. And the tricks you need are, first of all, you work in the Heisenberg picture or in an interaction picture, and you work with observables that have a very specific time dependence, a time dependence which has a covariant form. For example, this time dependence. This is a typical creation operator of a particle at some position. And if you write it in the Heisenberg picture, you have something like this, where x0 is the time and p0 is the energy. And so in this way, you recover covariance for the observables. Actually, the creation operator is not an observable. You obtain covariance for the operators in quantum field theory using this first trick. But of course, the operators are not enough. So in quantum mechanics, you need both operators and states. The states are not covariant. And there's no way you can make them covariant using these kinds of tricks. But what quantum field theory does is a state that is not covariant, because states are not covariant, but is invariant. So you take a state, like the vacuum state, for example, that's a typical choice of state in quantum field theory. it is invariant for Lorentz transformation. So if you do a Lorentz transformation of the vacuum, you still attain the vacuum because it's invariant for the Hamiltonian evolution. And so using these two tricks, using observables which have a covariant space-time dependence and using states which are invariant for Lorentz transformations, then you can say that quantum field theory becomes covariant, even though the observables in general, the general observables of quantum field theory and the general states of quantum field theory are not covariant. Okay, so you see the relativistic covariance in quantum field theory is something very delicate. Now, let's come to our proposal, our approach, which we called geometric event-based quantum mechanics, GEB in short. And the idea, as I was saying, is to consider quantum events as fundamental. Instead of considering quantum systems as fundamental, we consider quantum events as fundamental. And then we can create a Hilbert space for quantum events, observables for quantum events, and so on and so forth. But of course, if you consider events as fundamental, then you need to give a prescription for quantum systems, and they are derived. They are an emergent quantity. And as we will see, it will be clear in a minute, but let me just say it first. A quantum system is basically a quantum state for a succession of events in quantum spacetime, okay? Remember, in relativity, the definition of a system is a succession of events. Now, the definition of a quantum system is a quantum state for a succession of events. Okay, this is the basic idea of geometric event-based quantum mechanics. So even if you don't understand anything else, if you lose myself, if you lose me and the rest of the talk, if you remember this, I'm happy. So now, what is a quantum event? Of course, an event is something that is a point in space-time, and so it must have a position in space-time. But if you think about it, it also must have some energy and some momentum. Because if you don't have energy, nothing can happen. And if you don't have momentum, you cannot localize anything. Okay? So without energy, nothing can happen, and without momentum, nothing can be localized. So in addition to having a position in space-time, an event must also have some energy and some momentum. So this means we can assign to an event, we can assign some basic observables, which are the position observable in space-time. So the position observable in quantum mechanics would be just x1, x2, x3. So in the three-dimensional space, here we are considering a four-dimensional position observable, which also contains time. Okay, so time is an observable, just like before, like in the non-relativistic case. And also we need to introduce a four-momentum observable, an observable which has the three dimension of the momentum plus the zeroth dimension, which is energy. Okay, when I put a bar over something, it means a covariant four vector. Okay, it's a short notation for indicating covariant vectors. Okay, now that we have the basic observables, we introduce the canonical commutation relations between x and p. Okay, and they are just the extension of the usual canonical commutation relation, but here we need to introduce also the canonical commutation relation between x0 and p0. So now, and you see, we put the metric, the Minkowski metric here in the commutation relation. Why are we doing that? That's very simple, because we want to satisfy the Poincare algebra with m nu nu is just the four-dimensional momentum, which is the generator both of the rotation in space, if you just consider the spatial part of this m mu nu, but if you consider the temporal part of this m mu nu, you get the generator boosts. Okay, so this m mu nu is just the joint generator of rotations and boosts in spatial relativity. And if you impose this canonical commutation relation, then you get the Poincare algebra, exactly what we want. Okay, now this is the reason for this canonical commutation relations, but this also introduces the Hilbert space for our quantum events. And because of these canonical commutation relations, you see immediately that the Hilbert space for the quantum events is L2 of R4. Okay, so it's an infinite dimensional space, just like we would expect. So space-time is infinite dimensional. Sorry, infinite dimension. It's infinite, not infinite dimension. It has 4 dimensions, but it's an infinite in extension. Okay, here I'm just talking about spatial relativity. Okay, we will talk about general relativity maybe in the next conference or maybe in 20 years from now. Okay, now we can, now that we have, are you still with me? You're following me?
Yes, absolutely.
Great, thanks.
In the same space-time, yeah.
Okay, great. That's good. Sorry, I keep interrupting,
no,
but I don't have any feedback. So
fine. Yeah, good.
Okay, good, great. Okay, now we have a space-time. Sorry, a Hilbert space for space-time, a Hilbert space for events. We can construct a state, a quantum state for an event. Okay. And this is the quantum state written in the position representation. These are the eigenstate of the 4-dimensional position that I introduced in the previous slide. This is the momentum representation. So this is the eigenstate of the momentum observable that I introduced in the previous slide. And of course, these are just the amplitudes, the wave functions for this situation. Okay, in contrast to normal quantum mechanics, these are 4-dimensional amplitudes. They refer both to the spatial degrees of freedom and to the temporal degrees of freedom. So they are 4-dimensional. And of course, the position wave function is connected to the momentum wave function using a 4-dimensional Fourier transform. Okay, it's very straightforward things. Just a straightforward extension to the 3-dimensional case of non-relativistic quantum mechanics. But notice that here we're doing everything in a special relativistic way. And of course, we can extend the Born rule. Okay, it's the square modulus of the wave function. And this gives you the probability that the event we are considering happens in the space-time location x. Okay, so it happens at the position x at the time x0. Okay, so this is a Born rule that not only involves the position, like in the usual quantum mechanics, it also involves time. And notice that now it's completely unconditioned. It's not conditioned on time. It's an unconditioned probability that the event happens in the space-time position x bar. Okay, it's a space-time. So let me emphasize this. This Born rule probability is unconditioned. This is the JEB, the geometric event-based, our theory. Whereas in quantum mechanics, the Born rule is conditioned. Okay, why is that? Because you're using conditioned states in the Schrödinger picture, or you're using conditioned observables in the Heisenberg picture. So you get a conditioned probability. It's the probability that the particle is at position x, given that the time is, it's a conditional probability in quantum mechanics. In JEB, it's an unconditioned probability, okay? And this is important because in quantum mechanics, the probabilities are not covariant. In some quantum field theory textbooks, you find the statement that quantum mechanical probabilities are covariant. That's wrong. That's simply wrong. Because quantum mechanical probabilities are conditional probabilities which are conditional on time. So you need a foliation to define them, so they are not covariant. You need a foliation. Whereas in our case, in the Jebb case, we are using unconditioned probabilities, so they are covariant. I mean, you see, they all depend on covariant quantities. You have no explicit dependence on time separately from space. And there's another interesting thing that comes out from the commutation relations, and it's the uncertainty relations. You remember the Heisenberg-Robertson way to derive the uncertainty relation starting from the commutators. If you do that from these commutators, then you get these uncertainty relations. Of course, for mu equals 1, 2, 3, they are the usual uncertainty relations, so nothing new. The interesting thing is, consider the case of mu equals to 0, okay? This is a Heisenberg-Robertson inequality that connects the time at which an event happens with the energy connected to this event. In quantum mechanics, this uncertainty relation is completely meaningless. It has no meaning. In quantum mechanics, and this has been pointed out many times before. For example, in the book by Asher Perez, you find that this is a completely meaningless thing. And it comes from a paper, not very well-known paper about from Aharonov and Bohm, the same Aharonov and Bohm of the Aharonov and Bohm effect. But they wrote a paper on the time-energy uncertainty relation, which is very nice. And what they say is that this uncertainty relation is completely meaningless. And it's true. In quantum mechanics, it's completely meaningless. In our theory, it's not meaningless, because in our theory, what this is saying, our theory refers to events, remember, not to systems. So in our theory, what this is saying is that you cannot localize an event in time unless it has an energy spread, okay? If the event has a definite energy, then you certainly cannot localize it in time. Okay, so this is a true Heisenberg-Robertson type of inequality. Okay, another thing which comes about very easy in Jebb is Lorentz transformations. And a Lorentz transformation, I'm not going to show you the math, you can find it in our paper, but it's very straightforward. It's easy to see that it's just a unitary transformation acting on the Jebb state. Okay, so this phi is the state in the reference frame O, and this phi prime is the state in the reference frame O prime. And the connection between these two states is just a unitary, transformation. And this is just what Wigner's prescription of how to describe the symmetries of a theory, going from one state to another state. Okay, and you can give also a nice picture going from the reference frame in which you have x, z, and t, to a reference frame in which you have x prime and t prime. It's a hyperbolic transformation. So you go from psi or phi to psi prime by doing a hyperbolic transformation. And a hyperbolic transformation in space-time translates with a unitary transformation, which is generated by the four-dimensional momentum m mu that I was showing before. What happens in quantum field theory? You never find how to do quantum Lorentz transformations in quantum field theory. If you open any quantum field theory textbook, they never tell you how to do that. Why? Because it's a nightmare. You basically need to re-quantize from the start in a new reference frame. You have to start from scratch. Rerun the whole quantization procedure, because you need to impose equal time commutation relation, equal time. Time, of course, depends on the reference frame. So you really need to start from scratch. You throw away all your calculations, you go back to square one, you requantize from the start. Or maybe you can just use our results and take a shortcut from JED. And in our paper, I can show you how you can do Lorentz transformations in quantum field theory, because I'm going to show you how you can connect JED to quantum field theory. So, and in JED, Lorentz transformation are just unitary transformation. So you can make this connection and then do a Lorentz transform in JED and go back. And this is easier to requantize everything. So this is a good motivation already for looking into this new framework, our JED frame. Up to now, I've shown you a single event. You can extend this to multiple events using tensor products. If you have a fixed number of events, n, you just take tensor products of n events, and you can write a joint system, which can be entangled, of course, between these n events. Or maybe if the number of events is not fixed, you can even use a Fock space. I will not go into the details, you can find them in our paper, but you can use a Fock state by introducing some creation operators which act on some four-dimensional vacuum state and create an event at the position, at the space-time position x1. And this is the creation operator that creates an event at space-time position xn. And of course, these joint probability amplitudes, using the Born rule, you take the square modules of these probability amplitudes, give you the joint probability for the n events to happen in space-time position x1 through xn.
Sorry,
notice, sure.
Lorenzo, what are the sigmas here?
Oh, sorry, the sigmas are in case you want to introduce spin quantities.
Okay.
Spins. Yeah. Yeah, I'm not going to talk about that. Yeah, sorry, I copied and pasted the formulas from my paper. In the paper, we have spins. Okay. So these are just place marks for spins. I'm not going to talk about this stuff. Yeah, but you see that if you look at joint probabilities, then each event has its own time, okay? So these x1, xn, each event has a different time, which is important because if you try to do the same trick, and Dirac tried to do that, he tried to do the same trick using conventional quantum mechanics, and he runs into trouble. Because if you consider these as positions of the particles, how do you interpret the fact that each particle has a different time? That's really not, and indeed, if you look at Dirac's paper, he really doesn't know what to do with that. He artificially puts all the time at the equal, but there's no reason for doing that, and so on and so forth. But if you consider these x1 as position, xn as position of events, then it's obvious that they need different times. So I was saying you can have Fock spaces, and you can introduce different commutators for these creation operators, depending if you have bosonic or fermionic events. I mean, these are the usual commutation relations for if you have bosons, you want that the commutator within the annihilation and creation operator is a delta. If you have fermions, it's the anti-commutator, which is a delta. And if you impose this, and then you use bosonic events to introduce bosons, you get the correct commutator relation. And if you use fermionic events to get fermions, you get the correct commutation relations for the particles. Remember, particles are just a state of a sequence of events. I'm going to show you that explicitly in a minute. For now, just consider the commutators. Another thing which is important to point out is this 4D vacuum I'm using is different from the 3D vacuum of quantum field theory. The 3D vacuum is telling you that there are no particles at some time t0. If you work in the Heisenberg picture, this is telling you there are no particles at time 0. This 4D vacuum is telling you that there are no events at any time. So it's a different interpretation, you see. And actually, in order to get the 3D vacuum, you need to consider an event state of 0 for momentum. So you create an event which has 0 for momentum because you want to create the ground state of the field to get the 3D vacuum, okay? So these two, the 4D vacuum and the 3D vacuum, are completely different states. Now, of course, to connect quantum field theory from to Jeb, you use constraint, just as in the constraint version of the Wheeler-DeWitt equation I was telling you about. How do you do that? Well, start from let's consider a very simple case, a single particle, okay? Then we can extend this to the multiple particle case. So in quantum mechanics or in quantum field theory, a single particle is connected to a single particle wave function, okay, which is normalized so that at each time t, the square modulus of this psi integrated over x is equal to 1, okay? And this is the probability amplitude of finding the particle at position x, given that the time is t, okay? It's a conditioned quantity. The state in quantum mechanics is conditioned. And now you can construct a Jeb state from this conditioned state. You just simply promote this T as a quantum degree of freedom, okay? And then you can construct a quantum state using this wave function, okay? This exclamation mark is just to remind you that if you use the normalization of quantum mechanics, this is not going to be a normalized state in quantum mechanics. This is a technical point, but people might be confused by it. This state is not normalized because we are using the normalization of quantum mechanics. So you see that this Jeb state for a particle is a Jeb state describing the whole dynamics of the particle at all times as a single state of a sequence of events at all times, okay? So this is how you connect Jeb to quantum field theory. And of course, you can do it in a more elegant way by using a constraint operator. And the reason why I introduced constraint operators is because we need them. For the single particle case, this is not necessary, but if we want to do more complicated things, then it becomes necessary, okay? So this is how you get quantum field theory from Jeb, okay? Or Jeb from quantum field theory. Okay, so as I was saying, if you want to do analyze more complicated quantum field theory systems, then you need the constraints. In our paper, for example, we show a Klein-Gordon equation, and you use this kind of constraint, or the Dirac equation, you need this kind of constraint, and this is for the single event case. You can do replacing this operator with a number operator. You can extend this to Fock space, and I mean, it becomes very quickly very technical. I mean, this took us many years of work, but the main idea is just this: use constraints, and you can get quantum field theory, like Klein-Gordon and Dirac equation. Okay, my time is almost up, so let me conclude. I started by talking to you about time and quantum mechanics, how you can quantize time by promoting time to a quantum degree of freedom, which has its own observables, its own Hilbert space. And then I've shown you how the dynamics can be introduced by using constraints, like in the Wheeler-DeWitt or the Page and Withers mechanisms. And then I've shown you, those are all non-relativistic situations. And it took us many, many years, because it's really complicated, to extend these situations to a relativistic setting. And this is what geometric event-based quantum mechanics does. It's a completely new approach to relativistic quantum mechanics, which starts from quantum events, takes quantum events as the fundamental entity, and then builds up on that. And I've shown you that once you start from that idea, you can introduce observables. I've shown you like position, the 4 position observables, so observables both for the position in space and the position in time. And you can introduce a Hilbert space. You can introduce for the events. You can introduce a Fock space for events. You can introduce bosonic and fermionic events, which give rise to bosons and fermions once you connect events to particles. And then I've shown you how you can get quantum field theory from Jeb. I've shown you the case of Klein-Gordon, how you can get Klein-Gordon equation and Dirac equation, but of course this can be generalized to more complicated quantum field theory situations. And the take-home message is I've shown you a new approach to relativistic quantum mechanics. This is the paper we just posted last week, and this is my email address if you have questions. Thank you for your attention.
Thank you very much, Lorenzo, for a fascinating talk. So let me open up for questions. And there is a comment that's beautiful, but is there a question? So you should extend.
Hi. Can I ask a question?
Yeah, please go ahead.
Yes. So you showed that the events, the quantum events the events are quantized. So how, like, if there are 2 events there, suppose they are disjoint sets, or suppose there are some similarities between them. So have you thought about how do they interact between like the 2 events and their causal structure?
The causal structure, okay, sure. No, for now we consider only non-interacting, the non-interacting quantum field theory, which was already extremely complicated. Once you put interaction there, as you know, also in quantum field theory, things become much, much, much more complicated. So no, we don't know what happens in that case. We do have a way to treat this situation, which is basically an extension of what we did in our quantum time paper. Well, it would take me too long to go into the details here, but in our quantum time paper, we just basically considered the situation in which we have successive measurements on the same system by considering joint, by going to the time at which you do the last measurement, and then by considering a joint measurement on the system and on the memory degree of freedom that was storing the measurement outcome of the first system. I mean, really, I'm not doing a good job of explaining this, but if you go into our quantum time paper, you can find it there. And I'm pretty confident that the same thing can be done also in a relativistic setting, but we still haven't done that yet. It's certainly one of the first things we're going to do now.
Sure. Thank you. That was great. Thank you.
Sure.
Other questions? So I see that there is a comment / question, which may also be related to something which I had in mind. But the question from Ramesh Kumar says, usually assume that space-time is continuum. Can one give an example of a discrete space?
Oh, okay. Yes, yes. I was looking at this chat. Okay.
Yeah.
Yes, that's a very good question. Yes. So up to now, I've considered, I've shown you continuous spacetime because I was interested in recovering quantum field theory. But it's not too difficult to consider a discrete spacetime. How do you do that? The idea is, instead of considering continuous variable x and p observables, so x, I remember, is the observable for the 4 position. The position in spacetime, and p is the observable for the 4 momentum. We can consider a discrete, a theory in which both these observables have discrete spectrum. Okay, and then of course the commutation relations will change, and so on and so forth. But that will give you a discrete spacetime, not only in spacetime, but also in momentum, in 4 momentum space.
Like something like what Schwinger did for just the usual quantum mechanics with periodic boundary conditions and position and momentum.
Exactly.
Now you would also extend it in time.
Exactly. Perfect.
So do you also think that there would be new phenomenon coming from such a theory?
Oh yes, I really hope so. Yeah.
So
I still
like,
haven't found any.
Yeah. Okay. Also because well, I don't know what it would mean for a cyclic time if you were to just pursue that thing about discrete time, and if you were to put periodic boundary conditions on that.
In our quantum time paper, we did consider some other possibilities about that. That was not in a relativistic setting, it was in a non-relativistic setting. And we analyzed situations that maybe can describe situations such as maybe time just starts at some point. If you look at our cosmology, we have a Big Bang where time starts. So can you give a quantum description of a situation where time just starts from at a certain point? And in that paper, we had something like this. So, and of course, you can also consider periodic time and so on and so forth, which is kind of weird.
Yeah.
But yeah, you can do that. Yes.
All right. Thank you so much, Lorenzo. I think if there are the last chance to ask a question, I leave a few seconds window open for. Doesn't I think the opportunity has passed. So let's thank